When confronted with real-world probability questions, it's not often going to be the case that we're able to directly write down our answers or even directly reason ourselves to the answers. And that's because probabilities get very complex in the real world very quickly. And so what we really need are techniques that are going to allow us to break these down into smaller pieces that we can actually directly solve, and then recombine all of that to get the right answer. And probably our most useful tool for doing this is going to be the law of total probability. So the law of total probability is a result that enables the calculation of marginal probabilities using either joint probabilities or conditional probabilities. And we'll see how that exactly works today. So suppose that we have some partition of our sample space, which we'll just call E1 up to EK. Now, for any arbitrary event A, what we can do is we can use that partition to rewrite the event A. And so A can be written out as the union of A intersected with every bit of our partition. So this is what part of A intersects with the first part of the partition, and then the second part, and so third part, and so forth. And we do that across our whole partition here. Now, because every time that we look at A intersect EI, all of these are going to be disjoint. They're all going to be mutually exclusive. There's no overlap between any of these because all of the EIs themselves are disjoint, right? So the EIs are going to form sort of, if we think about our whole sample space here, right? The EIs are sort of cutting up our sample space like this. And then we can draw in our event A, right? A is going to be some sort of blob in our sample space. Okay, and so then if we look at it, right, E1 and A form this first part, and that has no bearing on our second part, E2 with A, or E3 with A, and so forth, right? And so because of that, they're all disjoint. And what that means is that we can write down the probability of A is going to be the probability of this union here, right? And that's just coming from us rewriting A using this expression that we have right here. But then because each of these events is going to be disjoint, right? Because each of them is mutually exclusive, we can use additivity to rewrite it over like this. Okay, and so what that allows us to do is it says, okay, instead of working with the probability of A directly, what if we instead work with the probability of A and EI for all of the different i's? Right? This is what we call the law of total probability, this mathematical relationship right here. And really this is coming from the use of a partition to rewrite the event A. Now, why is this a useful result for us? Well, sometimes it's going to be easier for us to directly infer joint probabilities. However, very commonly, it's going to be easier for us to directly infer conditional probabilities. And so why does that help us? Well, remember that the joint probability of A and B can be written as the probability of A given B times by the probability of B. This uses the multiplication rule for probability here. Okay, and so as a result, what we can say is that if we know our law of total probability normally allows us to write the probability of A as the sum of all of our joint probabilities, well, this is exactly the same thing as the probability of A given EI times by the probability of EI. And so now what we're doing is we want the marginal probability of A. If it's easy for us to come up with the probability of A given EI and the probability of EI itself, well, then we can get back to the probability of A using this other information here. And that's very often going to be a pattern that comes up. So if the marginal probabilities relating to EI are available and they provide enough information about A, this tends to make it easier for us to compute the probability of A than trying to do so directly. So when should we use this? When do we know we need to use the law of total probability? Well, so many scenarios where we're going to use the law of total probability, there are many scenarios where we're going to use the law of total probability. And oftentimes you can work this out if you think to yourself, well, it depends. If you are asked for a marginal probability and your initial answer is to say, well, it depends, then that's a hint that maybe you need to use the law of total probability. And so let's look at some examples of what we mean by this. So what's the probability that the second card dealt is an ace? If I'm dealing cards out, right, and I want to know not what's the probability that the first card dealt is an ace, but what's the probability that the second card dealt is an ace? And maybe your gut tells you, well, it depends on what we had as our first card, right? So what was the first card dealt? And so actually we can answer this question using the law of total probability fairly easily. Now, what about the probability that you get an A on an upcoming exam, right? So if I just asked you, well, what's the probability you get an A on an upcoming exam? Well, you might say it depends on the number of hours that you studied for. Right? And if you know how many hours you study, this becomes an easier question to address. What's the probability that an online order arrives late? Well, this is going to depend on what delivery company is shipping, where you ordered the package, whatever other piece of information might be relevant here. Okay. What's the probability that a hockey player scores on a breakaway? Well, it's going to depend on who that player is or who the goalie is that is playing against. Right? So in this case, again, we could use the law of total probability. Anytime we say it depends, what we're really saying is the conditional information is easier for us to work out. And because the conditional information is easier for us to work out, the law of total probability is going to be useful for us. So let's take a look at an example here. Suppose that we have a bag that is filled with dice of different sizes. We have 46-sided dice, 30 20-sided dice, 20 4-sided dice, and 10 8-sided dice. We're going to select a die out at random, and then we will roll it. We want to know, well, what's the probability that a 1 is rolled? And if you're just asked this question, right, what's the probability that you roll a 1? Your gut might tell you, well, it depends on what die we select. Because if we select a 4-sided die, the probability is 1 in 4. If we select a 6-sided die, the probability is 1 in 6. If we select an 8-sided die, the probability is 1 in 8. And if we select a 20-sided die, the probability is 1 in 20. And so it depends on what die we selected. And as soon as you're saying that, as soon as you have that thought, you should be thinking the law of total probability is relevant here, right? It depends on what die is selected. And so how can we use the law of total probability in this way? Well, what we can notice is that if we use, say, D4 means that we selected the 4-sided die, we use D6 as the 6-sided, D8 as the 8-sided, and D20 as the 20-sided die, right? If we take the union of all of this, this gives us our sample space, and all of these are going to be mutually independent of one another, or mutually exclusive with one another, rather. And so these form a partition. And so then what we can say is, well, the probability that we roll a 1, which I'll just call A here, is going to be the probability that we roll a 1, given we selected the 4-sided die, times by the probability that we selected the 4-sided die, plus the probability that we roll a 1, given we selected the 6-sided die, times the probability we selected the 6-sided die, plus the probability that we roll a 1, given we selected the 8-sided die, times by the probability we selected the 8-sided die, plus the probability that we roll a 1, given we selected the 20-sided die, times by the probability that you select the 20-sided die. And so working through all of these probabilities, this is just writing out that formula that we have, right? It's the conditional probability conditioned on each part of our partition times by the marginal probability of each part of our partition. And the good thing is all of these conditional probabilities are easy for us to work out, right? It's going to be 1 in 4, 1 in 6, 1 in 8, and 1 in 20. And all of these marginal probabilities are also easy for us to work out, right? Because we know that there are going to be 24-sided die. We know that there are 46-sided die, 10 8-sided die, and 30 20-sided die, right? That gives us 100 total dice. And so as a result, we use all of this information here. Okay, so how does this all come together? Okay, we can partition based on which die we are selecting, right? D4, D6, D8, or D20. And so then A is going to be the event that a 1 is rolled. So we take conditional probability times marginal with rolling a 4, or with selecting a 4, conditional times marginal with selecting a 6, conditional times marginal with selecting an 8, and conditional times marginal with selecting a 20. And then again, we have 1 out of 4 chance if you've selected the 4-sided die, times by a 20 out of 100 chance of selecting the 4-sided die. 1 out of 6 chance if you select the 6-sided die, times 40 out of 100 of actually selecting that die. 1 out of 8 with the 8-sided, times 10 out of 8, and then 1 out of 20 times 30 out of 100. And if we work all of that out, that gives us about a 14.4% chance, right? So if you're playing this game, there's about a 14.4% chance that you roll a 1. Now, part B, what is the probability that a 6 or higher is going to be rolled, right? Now, again, it's going to depend on what die we select, but it's going to depend on which die we select in exactly the same way that we just saw, right? So we can use essentially the same argument. We partition on which die we are selecting, right? A is now the event that we roll a 6 or a higher. Okay, and so then we can say, well, it's the conditional times the marginal, conditional times the marginal, conditional times the marginal, conditional times the marginal. Right, we add all of those up. If we select a 4-sided die, there's a 0 chance that we do it. If we select the 6-sided die, only 1 out of the 6 options is going to give us something higher, at least 6, a 6 or higher. 3 out of the 8-sided dies, or 15 on the 20-sided dies. And so then if we work all of this out, this tells us that there is about a 33% chance, 32.92% chance that we roll a 6 or higher. Okay, and so again, as soon as we're saying, well, it depends, we should think to use the law of total probability. Okay, so we can take a look at a different example here. Suppose that we're dealing 2 cards dealt. We're dealing them face down. We want to know what's the probability that the second card dealt is an ace, or is a heart, rather. And so immediately we think, well, it depends on if you deal a heart or not on your first card. Right? And so what we can do is, well, we can say heart union heart complement can form a partition as our initial space, where H is the event that you draw a heart on your first card, and H complement is that you don't. Right? So then we can say, well, what is the probability that the second card is a heart? This is going to be the probability that the second card is a heart given the first one was, times by the probability that the first one was, plus the probability that the second card is a heart given the second one wasn't, times by the probability that the second one wasn't, right? Or sorry, times the first one wasn't. And so what's the probability that the second card is a heart given that the first card is a heart? Well, in this case, we are going to have 12 hearts left in the deck, right? There are 51 cards left in the deck, and so we can just write that down. What's the probability that our first card selected is a heart? Well, there are 4 suits. Each suit is equally likely, right? So we can either write that as 13 out of 52 or 1 in 4, right? That's the same thing. I'll just do 13 out of 52. And then for our second value here, right? What's the probability that we select a heart if we did not select a heart on the first time? Well, that's going to be 13 out of 51. And then what's the probability we do not select a heart on the first draw? That's 3 out of 4, right? There's 3 out of 4 chance you don't select a heart. Again, if you actually work out what this is going to be, what we'll find is that this simplifies down to 1 out of 4. Okay, and so it's actually equally likely that it's a heart on the second draw as it is on the first draw. Okay, so it depends on whether the first card is a heart or not. And so if it is a heart, then we know that we have a 12 out of 51 conditional probability of the second one being a heart. If it's not, then there's a 13 out of 51 chance. Okay, so taking H and H complement to be the partition, then we have the probability that we have our second card being a heart is broken down using the law of total probability here. Right? We have 12 out of 51 times 1 in 4, 13 out of 51 times 3 out of 4. That gives us 1 out of 4. Now, intuitively, we could have worked out that this would have been 1 in 4. And the reason is, what if I had asked you for any of the other suits instead? So what's the probability that the second card's a diamond? What's the probability that the second card's a club? What's the probability that the second card is a spade? And all of those have to be the same probability, right? Because one of them is not going to be more likely than the other. And so as a result, we could have gotten 1 out of 4 that way. But if you want to really formally prove it to yourself, the law of total probability is going to allow you to take that impulse to say, it depends, and actually turn it into a marginal probability. Let's look at some more examples here. So suppose that a package is being ordered from an online retailer. The retailer uses delivery company A 10% of the time, and otherwise they use company B. Company A delivers packages late 75% of the time, and company B delivers packages late 15% of the time. So what is the probability that the package actually arrives late? So we want to know, well, what's the probability that we have a late package? Okay, and it depends, right? What does it depend on? Well, it depends on which company is actually going to be sending us the package, okay? And so as a result, what we can say is, well, this is going to be the probability that it's late if A sends the package, times by the probability that A sends the package, plus the probability that it's late if B sends the package, times by the probability that B sends the package. Right? And so this is our law of total probability. A and B are the only 2 companies used, so they form a partition of the space, right? And this is going to give us an expression for our marginal probability here. And then the nice part is we actually know all of these different terms, right? So we say that the probability that A sends the package is 10% of the time. And if A sends the package, then it's late 75% of the time. So that's 0.75 times by 0.1 plus, right? If B sends the package, it's going to be late 15% of the time, so that's 0.15. And then how much does B send the package? Well, they send everything that A doesn't, so that's 1 minus 0.1. Right? And then we could fill this in on our calculator here and work out what this actually is going to have to be. Okay, and so what's the probability that the package is late? Well, it depends on which company delivers the package. So we partition on A and B being the two different possible companies as the senders. Okay, so the probability that A sends it is 0.1. The probability that B sends it is the same thing as A complement. And so that's 1 minus 0.1 or 0.9. L is the event that it is late, and so then we can write it down using our law of total probability here. So that's 0.75 times 0.1 plus 0.15 times 0.9, and that gives us 0.21. So there's a 21% chance of knowing that your package is going to be late, or 21% chance that your package is late. So without even knowing which company is going to send the package, there's a 21% chance that it will be late. This is going to factor in both the probability that it is late from the given carriers, but also the relative likelihood that each carrier takes it. So if we look at it, that 21% is a lot closer to the 15% than it is to the 75%, right? So it's a lot closer to the probability that B is late compared to the probability of A being late. And why is that? Well, A only sends 10% of all packages. B is sending 90% of all packages. And so without knowing anything, there's a 90% chance that B is going to be sending you your package, and that happens, or that would be late only 15% of the time. Okay. On the other hand, A is going to be sending the package only 10% of the time, right? So it's not very often, but when they do, there's a really high chance that it's going to be late. And so that's going to be pulling that average up. Okay, so we take a look at another example here. Suppose that a four-sided die is rolled and then a coin is flipped the number of times that is actually shown on that die. Okay, and so we can say if the coin is fair, what is the probability that exactly two heads are going to be seen? Okay, so we are rolling a four-sided die and then flipping a coin the number of times there. And so what are we thinking here? Well, we're thinking it's going to depend, right? And what does it depend on? It depends on whatever we happen to roll on our die. Right? Because if we know that we roll a 1, for instance, well, then this is impossible. You have to have at least a 2. But then if we roll a 2, then we're just asking what's the probability that we flip 2 heads in a row. And if we roll a 3, we're saying, well, what's the probability that of 3 flips, 2 of them are heads? And then if we roll a 4, we're saying, what's the probability that of 4 flips, exactly 2 of them are heads, right? So we can break it down based on all of those cases here. So we take our rolls to be a D1, D2, D3, and D4, right, to represent the result we actually get on our die here. Now, the probability that we have exactly 2 heads if we roll a 1 is 0, since you need at least 2 flips. The probability that we have exactly 2 heads if we flip a 2 is going to be 1 out of 4, and that's because if you flip 2 coins in a row, right, then there are going to be a total of 4 possibilities. We can get our head-head, we can get a head-tail, we can get a tail-head, or we can get a tail-tail, right? So this is 2 to the power of 2, okay? And so of these, exactly one of them is going to have 2 heads. Now, what about if we roll a 3, right? So if we roll a 3, how can we work this out? Well, then we are going to have either head-tail, heads-tails, or heads-tails, right? For each of these, we can get a heads-tails, heads-tails, or heads-tails. And so then we're going to have 2 to the power of 3 equals 8 total sequences of coin flips, okay? And how can we say, well, we want 2 of them to be heads, right? Well, we have to choose 2 of these slots, right? And so we have 3 slots. We want to choose 2 of them. So we can take 3, choose 2 out of 8. And that's going to give us our probability there. Okay, so probability of A given D3 is 3 choose 2 out of 8, which is just 3 out of 8. And then A given D4 is going to be 4 choose 2 out of 16, okay, for the same logic there. And so then what we have is the conditional probability of getting exactly 2 heads for all of the different numbers we might roll. Now we know that all of these numbers are rolled with exactly 1/4 probability, right? And so then we can take 1/4 times the first probability, 1/4 times the second, 1/4 times the third, 1/4 times the fourth to write this down just in a more compact way. We've factored out that 1/4, right? But this is 1/4 times this 1/4 times this, 1/4 times this, plus 1/4 times this, and all of that gives us 1/4. And so playing this game, there's a 1 in 4 chance that you're going to flip exactly 2 heads. Okay. Now, looking at sort of an even further example, right? We have 4 coins that have been placed in a bag. 3 of them are fair coins, and 1 of them has 2 heads. What's the probability that we flip a head if we are going to draw a coin at random from this bag and then flip it? Okay, well, at this point, we're starting to see the pattern, hopefully. It's going to depend on which coin we actually pull out of the bag, right? Because we can think about either pulling the fair coin or we can pull the not fair coin, which I'll just write as F complement here, right? So this forms a partition for us. And so then we can say, well, what's the probability that we flip a head if we pull a fair coin? Okay. And if we pull a fair coin, we know that there's a 1/2 chance that we are flipping a head. What's the probability we flip a head if we pull the unfair coin? Well, in that case, both sides are heads, so there's a probability of 1 that that's going to happen. And so then if we want to know, well, what's the probability that we flip a head in total? That's going to be A given F times the probability of F plus the probability of A given F complement times by the probability of F complement, right? And then we can fill in all of our options here. So A given F is 1/2. Probability of F, right? We know that 3 of the 4 coins are going to be fair, so that's 3 out of 4, plus 1 times by 1 out of 4. Okay, and so then that's going to be 5 out of 8, I think, if the math is done correctly there. Okay, and so we can walk through this argument again a little bit more completely. Okay, so it's going to depend on what coin we select. If we partition whether the coin is fair or not fair, right, that's going to give us the probabilities. The marginal probabilities are 3/4 and 1/4, respectively. Moreover, we know if it's fair, the probability you get a head is 1/2. If it's unfair, the probability you get a head is 1. So the probability you get a head is going to be 3/4 times 1/2 plus 1/4 times 1, which gives us 5 out of 8 probability. Okay. Last example that we're going to look at here. Suppose that we have a company that manufactures computer components and then it bins them based on quality. So 20% of the components are excellent, 60% are good, 15% are acceptable, and 5% are poor. The probability of failure of these components is going to be 0.01, 0.05, 0.15, and 0.4 for each of the different categories respectively. And so what we're going to do is we're going to say, well, what's the probability that if we select a component at random, it's actually going to fail? Okay. And so again, what's the probability that a component selected at random fails? Well, it depends on what type of component we select, right? Because we know if we select a highest quality and excellent quality, it has a 1% chance of failing. If it's good quality, it's a 5% chance. If it is acceptable, it's a 15%. And if it's a poor quality, then it's a 40% chance of failure, right? So conditionally, we know all of these things. And so then as soon as it depends, then we're thinking, well, why don't we use the law of total probability here, right? And so we can actually work through this full example. We're going to partition based on the quality of the component, either excellent, good, acceptable, or poor. And we're using an R for poor here so that we don't have an extra P floating around in our probability notation. And then we use our law of total probability, right? And we should be getting comfortable with writing this down now. We want the probability of F. So that's F given E times probability of E, F given G times probability of G, F given A times the probability of A, F given R times the probability of R. We were given all of these explicitly, right? So 0.01 times 0.2, 0.05 times 0.6, 0.15 times 0.15, and 0.05 times 0.4. Multiply that all through together, and that's a 0.0745. So 7.45% chance that a randomly selected component is actually going to have failure. So often it's going to be easier for us to infer conditional probabilities. There's many situations where the conditional probabilities are easy for us to write down, or comparatively easy, but the marginal probabilities are hard. Now, that does not mean we don't want the marginal probabilities. Very frequently, the marginal probability is exactly what we care about. And so the law of total probability is going to allow us to fix these situations. Right? The law of total probability applies whenever we think, well, it's going to depend on something to know the probability. And so then we ask, well, what is that thing that it depends on? We form a partition around it, and then we can use that information to actually calculate out a marginal probability. And so anytime you're being asked for a probability and you find yourself thinking, I think this probability depends on something, then you should condition on that piece of information and then use the law of total probability to actually work out the marginal. Because at the end of the day, the marginal probability never depends. That's what it means to be a marginal probability. It's going to be some fixed number, and the law of total probability is going to be what connects us from knowing that it actually does depend on other information to being able to tell us, well, what is the overall marginal probability in this setting?